Hello, everybody. So my name is Mark Moriarty. I'm a sales manager for LKAB. You'll notice that the title of the presentation is slightly different to what was advertised in the program. But the intention was always to talk about magna-dense concrete as a construction material for nuclear new builds and decommissioning. So first of all, I would like to talk about LKAB, the group. So if we have any Scandinavians in the audience or any Swedes, then you will probably be aware of LKAB. If you're outside of Scandinavia, the chances are you might not heard of LKAB, but we are certainly in the north of Sweden, one of the largest companies in Sweden. So the company has a long history of mining. We were established originally in 1890, so 130 years or so we've been mining iron ore in the Arctic Circle in Sweden. We are now 100% state-owned by the Swedish government. So globally we have around 5,000 employees. Predominantly we are involved in mining iron ore, although I will show you later, we do have involvement in a range of mineral applications. But in terms of iron ore, 80% of the iron ore that's mined in Europe is from LKAB. So you can see there in 2024, we had a revenue of about 33 billion Swedish krona. I think that equates to around about 3 billion euros. And then we mined or we supplied around 21 million tons of iron ore products. So the organisation is split into two divisions. We have the iron ore business, which, as I mentioned, is a large concern. It's by far the largest part of the organisation, and that accounts for around nearly 90% of what LKAB do. But I work for the special products division, and we're involved in a number of mining and mineral-related industries. And what I'm going to talk about is a particular product called magna-dense. A magna-dense is made from Swedish magnetite. So I don't know if we have any chemists or anyone that's interested in that type of discipline, but magnetite is an iron oxide. It's Fe3O4. So it consists mainly of iron oxide, FeO and Fe2O3, and it's a black iron oxide. It's relatively stable at room temperatures, but it will, or it can be oxidized at higher temperatures. It can convert to Fe2O3 or hematite, but that's accompanied with a slight increase in density and a slight increase in volume of around about 2%. So Swedish magnetite contains around about 70% iron by weight and has a particle density of around about 5 tons per cubic meter. And this is important because iron ore, or the weight of iron ore, is the reason why we use this particular material in the nuclear sector. It's relatively stable chemically. It is oxidized already, and further oxidation at room temperature doesn't happen readily. So in contact with air and water and most mild solutions, it's relatively inert. And it's non-radioactive. It doesn't have any natural radioactivity. So we take Swedish magnetite, and we, LKAB Minerals, we turn it into magna-dense, which is a specially graded form of magnetite used for construction. So magnetite aggregate is passive in concrete matrix, so that means it doesn't react, it doesn't affect the rheology during mixing. It's quite a hard and tough material, so it doesn't degrade during the mixing operation. It has good compressive strength, which obviously lends itself to good compressive strength of concrete. It has very high thermal conductivity for an aggregate, for a mineral, so it's able to absorb and store a lot of heat energy, which has some beneficial applications in the nuclear sector. And as I mentioned earlier, its distinctive black colour can be beneficial to identify its use in concrete. So the magna-dense that we supply is graded specifically for the construction industry. So we can supply aggregate conforming to EN 12620, which is a standard that covers aggregates for concrete. So in terms of grading, aggregate shape and texture, density, absorption, all those properties, we can test our aggregate in accordance with EN 12620. As I mentioned, we're sizing specifically for concrete, so the main grades for concrete aggregate are 20 millimetres down, 8 millimetres down, and 2 millimetres down. But we do have a range of fines for different applications. And as I mentioned, because it's non-friable, during the concrete manufacturing process, the aggregate doesn't break down. Some other high-density aggregates used for radiation shielding applications are more friable. They tend to break down during the concrete manufacturing process. And because of the consistency of Swedish magnetite, we're able to produce an aggregate that is very uniform in chemistry and properties. So magnedense concrete, if you decide to replace all conventional concrete aggregate with magnedense, you can achieve densities of up to 4 tons per cubic metre, which compared to standard density concrete of 2.4 is getting towards nearly twice the density of concrete. One of the benefits of high density concrete is you can use conventional concrete mixing equipment. So conventional batching plants, concrete mixing trucks, the standard concrete mixing equipment can be used. Obviously, because of the added mass, then you do need to be aware of more load on equipment, but nothing special is needed to prepare and place concrete. The only caveat with high density concrete is it's important to keep water content to an absolute minimum to maintain density. So you will need to use super plasticizers to achieve the density. But as a company, we can help construction companies, we can help designers formulate mixed designs to achieve all of these properties. So you're probably asking yourself, how does this all relate to nuclear applications? Well, we've been specified on a number of projects in Europe and globally for nuclear new builds and decommissioning projects, mainly because of the benefits that high density concrete can offer for nuclear applications. So obviously the increased density helps to achieve better radiation shielding, better attenuation properties. That enables in turn for thinner sections to be produced, so it can reduce the footprint of reactor buildings or decommissioning containers. And we can also supply, because we have a portfolio of minerals, we can supply neutron shielding materials for concretes, so we can effectively offer a complete solution for radiation shielding. I mentioned the low porosity and chemical stability. Many of you who are involved in nuclear construction will know now there is a requirement to build new nuclear power stations or nuclear installations with long design life, typically 60, 80, 100 years design life. And the stability of magnetite and magnedense helps that to be achievable with high density concrete. I mentioned the thermal properties of magnedense, so and its high heat capacity and thermal conductivity. So it's suited to a lot of emergency applications, such as reactor containment vessels or core capture facilities. The natural density of magnedense can help overcome hydrostatic pressure. So if you're putting a nuclear power station on some land and you're worried about hydrostatic pressure, then more mass with less volume is something you can achieve with magnedense concrete. And obviously the consistency and quality of Swedish magnetite ensures consistent properties, which is important for the nuclear sector. So its relevance to nuclear new builds. So if we look at SMRs to start with, obviously there's a lot of interest now in small modular reactors. I've used a stock image there which doesn't contain a lot of concrete, but we already know from engagement with the SMR industry that a lot of reactors use high density concrete or use concrete for the containment structures of the reactor buildings. So we're already supplying magnedense and high density concrete to new projects currently being constructed globally. And one of the benefits for SMRs, obviously the whole concept of SMR is to produce a small reactor. And one of the things you can achieve with the high density concrete is a smaller footprint. You can use thinner walls and still have the same level of radiation shielding performance. If you're looking to submerge or partially submerge an SMR or a reactor building, you know, the high density concrete means quite often it's possible that you don't need to excavate so much soil, so much earth, because higher density concrete will enable you to use a smaller volume of building. In terms of large-scale nuclear power plants, we've been specified already on a number of projects. You know, the EDF reactors currently being constructed in the UK, Hinkley Point and Sizewell have made use of Magnadents in their design and construction. We mine, as I indicated earlier, millions of tons of iron ore, so there's certainly no concerns with continuity of supply. We understand that large nuclear power projects are, you know, take several years to complete. You know, and that you might need the aggregate over that prolonged period of time, so we can ensure reliability of supply over a prolonged construction period. We have global stockpiles of the material, and we have a very good logistics supply chain to ensure continuity of supply. So we already have a track record. We've been supplying Magnadents for nuclear new builds and decommissioning for 30 to 40 years globally. So it's not a new material for this particular sector. But what I will say is that I believe there are a number of new applications that Magnadents would lend itself to perfectly. We need, or I need, to be talking to specifiers and engineers so they understand the potential benefits of high density concrete and high density aggregate so they can make more use of it. There's definitely a number of applications where I believe we are underutilised. So nuclear decommissioning in the UK, for instance, we've been supplying the nuclear decommissioning industry for more than 40 years with high density concrete for intermediate level waste containers, for overpacks, for a number of shielded buildings at Sellafield and other locations. So we have a long history, we have a track record, we can demonstrate that Magnadents is suitable for decommissioning. Unfortunately, in the UK, we haven't managed to progress a geological disposal facility yet. It's something, obviously, it's in the plans for the UK, but other countries are way ahead of us. You know, in Finland, in Sweden, that they are working or already have achieved, you know, much success in developing geological disposal facilities. But again, you know, I think it's an underutilised application area for Magnadents. I think, you know, less excavation, increased radiation shielded performance is something that we can offer the nuclear decommissioning sector. So I'll just quickly talk about one of the case studies. And we have a range of case studies or applications we can share with people. But I think for now, I'll just mention the core capture block at Hinkley Point C. So if anybody doesn't know, a core capture block is a large containment structure beneath a nuclear reactor. The idea post-Fukushima is to have a facility that can potentially capture a reactor in the event of a meltdown. And basically the idea is, you know, it's a large structure that's able to hold the melt for a certain period of time, and then the idea is to pump seawater or water into the vessel to cool down the reactor. So it's used in a number of particularly modern EPR designs. And Magnadents, particularly for the EDF designs, has been specified for the core capture block. So for Hinkley Point C in the UK, we supplied around about 4,000 tonnes of magnetite or Magnadents concrete for the core capture block. So just briefly, in conclusion, you know, I spoke about the mechanical properties and the durability of Magnadents, and those properties are very well suited for nuclear applications. And Magnadents concrete itself does support a lot of critical design requirements for new nuclear builds and decommissioning projects. So it's my job really to convey some of those benefits to nuclear industry professionals, particularly designers and specifiers. I think there are a number of industry professionals that we need to reach, and if they have the knowledge that MagnaDents is one of the tools in their armour to improve design, to make designs more effective, that's my job. So hopefully we can have lots of conversations at this event with specifiers and nuclear professionals to try and do that. So I'm not sure how I'm doing for time, probably a little bit ahead of schedule, but I can take questions now, but if anybody wants to, after the event, move next door, if there are any specific questions about MagnaDents, then please feel free to come and have a chat. Does anybody have any immediate questions now? No? Okay, good. Well, we'll be in the room next door anyway if anybody wants to come and have a chat. Thank you very much.